Okay, the whole thing from today was too long for me to post, so I'm gonna have to do this in two sections. But I'm just gonna very quickly re-explain what we did in class today. Okay, so we went over probability of independent and dependent events. Okay, in the first two boxes, we wrote down how the word or means you're going to add in probability. The word and means you're going to multiply in probability. And also, if it says you do something and then you do something else, where you're still doing both of them, so that's just like saying and. So the word then also means to multiply. So we talked about how you would do the probability of A or B means the probability of A plus the probability of B. And if it's the probability of A and B, then you do the probability of A and then multiply it by the probability of B. Okay, here's the part where we talked about probability is always between 0 and 1. 0 indicates being impossible, and a 1 indicates being certain. And it can be expressed as a fraction, a decimal, or a percent. The next part is the number line. So, if it's 0, it's impossible. If it's 50% or half, it's equally likely. If it's one whole, that means 100%, which means it's certain to happen. And then you have your little benchmarks that are in between there. So the numbers can be anywhere between 0 to 1, or anywhere between 0% to 100%. Okay, theoretical probability was when the chance of something happened under ideal circumstances. So that means it's basically what you expect to happen. And then we talked about the example of rolling the 4 on the cube. So since your sample space is 1, 2, 3, 4, 5, 6 on your cube, you have 6 total outcomes, which will be your denominator. And the one that you're looking for, which is the 4, there's only one of them. So that's where you get the 1/6 from. Experimental probability, remember, was when we actually perform the trials and then we record the results and we write our probability. So it's based on repeated trials and recorded results. And then they gave you this example of finding the experimental probability of winning a game, where you must play the game many times and then divide the number of games won by the total number of games played. So your probability would look like a fraction in this case, or in every case basically, but the total won over the total played is where the division comes in, because remember that this bar right here means division. Okay, then we have the other side, which started off talking about what an event is. And an event is, if it's simple, it's just a trial for an experiment. If it's compound, then that means 2 or more trials put together. So 2 or more simple events put together. So an example of a compound would be drawing the white marble from the bag first and then also drawing the red marble from the bag. Okay, if it was just simple, then you would just only be drawing the white, or you would just only be drawing the red. Okay, to find the probability of compound events, you multiply the probabilities of the simple events that make up the compound event. Now remember, you may also be adding. Just depends on if it says and or. Okay, independent means it can stand alone. It doesn't need anything else. Okay, if it is the probability of independent, then that means the first probability is not going to affect the second probability. So in your problems, you're looking for keywords such as with replacement, or it's going to say it was replaced, or it was put back, or something like that. If it's dependent, then that means it cannot stand alone. It needs help. Something else has to be there with it. that's going to affect, you know, the outcome of whatever's going to happen next. Okay, so the probability of dependent events is where the probability of the first event is going to affect the probability of the second one. So when your problems, in your word problems, look for words such as without replacement or not replaced or not put back. Okay, and then we did these 5 practice problems at the bottom. Choosing a card from a deck of playing cards and then choosing a second card would be dependent because you're going to choose that first card. It doesn't tell you you're putting it back in the deck. So when you choose the second card, you have fewer cards to choose from. So that first one affected the second one. That's why it's dependent. For number 2, tossing 4 coins at the same time is independent because you have 4 separate coins. Neither one is affecting either of the other ones. So you get your probability for the first, the second, the third, and the fourth all separately, and that makes it independent. Number 3, selecting 2 books from 6 books. So if I got 6 books total and I want to walk away with 2 different books, then that has to be dependent because once I pick that first book, my second book has to be different. I can't pick the first book twice. So therefore, after I've taken out a book, I've got less there on the shelf to pick from for my second book. So my first pick affects my second one. The second one depends on what I picked first. So that's dependent. Number 4, tossing a coin and spinning a spinner. We got 2 separate things, a coin and a spinner. Neither one has anything to do with the other, so they're independent. Okay, number 5, the team captain selecting 2 people to be on the basketball team. Okay, well, if I want 2 people to be on the team, I cannot pick the same person twice because nobody is 2 people in one. So therefore, I pick up the first person and then I have fewer to pick from that second time. So that means my second outcome depends on the first one. So that's dependent. Okay, the next page we talked about the fair cube being rolled. And in this situation, you want to go ahead and write down your sample space first. Since the number cube has 6 numbers on it, we wrote down 1, 2, 3, 4, 5, and 6. Okay, and then we looked at the probability of rolling a 5 or a 6. Sorry guys, this lighting has been crazy all day once I got to this side of the paper. Okay, I think that may be a little better. Okay, so the probability of rolling a 5, there's only 1 5 right here. So that's 1 out of 6. And since I want the probability of rolling a 6 also, there's only 1 6 out of the 6 numbers. So the word or means we're going to add. So you do 1 6 plus 1 6, which gives you 2 6. That simplifies to 1/3. And then you write the fraction, the decimal, and the percent. Okay, then we talked about the probability of rolling a number less than 7. So that's a less than symbol. Well, everything in our sample space is less than 7. So therefore, we will not have any numbers greater than 7. So all 6 out of 6 are less than 7. So that's 1 whole. So my fraction is basically 1 whole. 1 over 1 is 1. As a decimal, it's 1.0. And the percent is 100% because it's the whole thing. Number 3, we had the probability of rolling a 7. Well, look at the list. There are no 7s in the list. So we've got 0 7s out of these 6 numbers. So that's why we have a 0 probability. 0.00%. Okay. Then number 4, we had the hat with the 4 names in it. And it says, wearing a blindfold, Bethany is told to draw one name from the hat. Was the probability that she will draw a name that contains a letter A? The letter A. So remember I told you, you must write the P and put in parentheses what it's asking for the probability of. If you do not do it, you will be counted off. So since it says it wants the probability to contain the letter A, so it's the probability that the name contains A. So in parentheses, I put contains A. So since Jan contains A, Maria contains A, Manuel contains A, and Rob does not, that is 3 out of the 4 names that contain an A. Then I also wrote it as the decimal and the percent. Well, number 5 says Brandon's graduating class had 5 seniors that entered the Air Force, 7 entered the Army, 12 entered the Navy, and 4 entered the Marines. If one is selected at random, what is the probability that he or she is not going into the Army? So the word not meant to subtract. Okay, so it is specifically asking for the probability that the student is not going into the Army. So that means we put P and in parentheses we are going to put not Army. We're not going to the Army, something like that. So you first need to add up all of your numbers and you get a total of 28. Since we don't want the ones going into the Army, you now need to take that 28 and subtract the Army from there. So there are 7 going to the Army, so 28 minus 7 is 21 that are not going to the Army. So now we end up with 21 out of 28 going to the Army. I mean, not going to the Army. Simplifies to 3/4. Number 6, we had the probability, we had 12 cards, and we want the probability that the card will be striped. So we're going to write P in parentheses striped. So we want probability of a striped card. So we're going to count the striped cards, 1, 2, 3, 4, and we write it over the total of 12. Simplified to 1/3. Very simple. Number 7, we had Fiona with a box of red buttons, 5 red buttons and 9 blue buttons. She randomly selected one button. What's the probability that she picks a red button? So just wants the probability of red. So P with red in parentheses. So the total, 5 plus 9 is 14. So now look for your red buttons. It says there are 5 of them, so that's 5 out of your total 14. And that cannot be simplified. And number 8, the last one on this page, was during the 30-minute half hour of television programming, 8 minutes are going to be commercials. If the television is turned on at random during the half hour, what's the probability that a commercial is not shown? So again, not means subtract. So we need to get our total. And the total, since it said half hour programming, means we've got 30 minutes total. If I do not want the commercials in there, then I need to subtract out the 8 minutes of commercials. That leaves me with 22 minutes of non-commercial TV. So, in parentheses beside my P, I'm going to put not commercials. Okay, so that means since 22 minutes are not commercials out of my total 30 minutes of programming, then that means I can simplify and get 11/15 for my probability of not watching commercials. Okay, the next page started our independent probability. And again, at the top, we just wrote down or means to add, and means to multiply. If it says then, that's the same as saying and. So you would also multiply there. If is independent, it stands alone. If it is independent, then that also means the total stays the same, denominator stays the same because it is with replacement. First probability does not affect the second. Okay, when it says what about the probability of two independent events, that means you need the product of each event. Or you may even use the sum. Depends on if it says and or. Okay, so we did these practice problems, 1 through 5 here. And the first one said, how many outcomes are in the sample space? So since we were using this spinner and this cube, then the spinner has 4 outcomes. The number cube here has 6 outcomes. So remember, the easy way to find your total outcomes is use your fundamental counting principle, which says you can multiply the outcomes on each event. So 4 times 6 gave you 24 outcomes total. Number 2, we want the probability that the die shows a prime number. So that's P with prime number in parentheses. So in this situation, you have to write out your sample space first. Since it's a die, we know that 1, 2, 3, 4, 5, and 6 are on the die. Now go and find the prime numbers. The prime numbers are 2, 3, and 5. That's why those are circled in this case, because they're the prime ones. So that is 3 numbers circled out of the 6 numbers totaled, which is equal to 1/2. Number 3, the probability of getting a B on the spinner and a 4 on the die. So since we look at the spinner and we see 1 B out of these 4 numbers, that's why we have 1/4 here. It says and, so that means we're going to multiply, and then we look at the probability of getting a 4 on the die. Well, if you go back to your sample space, and I'll even rewrite it in case these circles are throwing you off. When we look back at this sample space, there's only 1 4 out of the 6 total. So therefore, that's why the probability of the 4 is 1/6. So once you multiply, you get 1/24. Number 4, we want the probability of getting a consonant on the spinner and an odd number on the die. So when I look at the spinner, remember consonants are anything except A, E, I, O, or U. So since I have an A, that's a vowel. Take it out. So B, C, and D are your consonants. So there are 3 consonants out of the 4 numbers. So that's where the 3/4 comes from. Now, odd number, go back and look at your sample space. 1, 2, 3, 4, 5, 6 on your die. And your odd numbers are 1, 3, and 5. So therefore, we have 3 out of 6 that are odd, which simplifies to 1/2. So that's why I have 1/2 written here. So the 3/4 times 1/2 gives you 3/8. And notice I even wrote it down right there as well. Okay, and number 5, we want the probability of a vowel. Well, since 3 were consonants, that means only one was a vowel, which was the A. So that's why we have 1/4. Oh, and don't forget to write your information in the parentheses. So for the P of vowel and number greater than 6. Those are your key words. So there's one vowel out of the 4. And when I look at my sample space of 1, 2, 3, 4, 5, 6, nothing there is greater than 6. So therefore, there is no way we have 0 out of 6 chance, which is just 0. And anything times 0 is 0. And the reason why the whole thing is 0 because it says vowel and number greater than 6. We can't get them both together at the same time. So that means we have no chance of getting this whole probability. Okay, the next page, we discussed our dependent events or dependent probability. Again, we wrote that or means to add, and means to multiply. Then is the same as saying and. Okay, here we talked about how dependent, remember, means it cannot stand alone. You need help. Something has to go with it. So, in your problem, look for it to say something like without replacement or not put back. Okay, the first probability affects the second probability. So in this case, because of that, your total changes. Because remember, if I pull something out of the bag and I don't replace it, I have one less item in the bag the second time around. So my denominator is going to be different. Now, depending on what the probability is, the numerator may also change as well. So you got to look out for that as well. Okay, we had the 2 examples. Now, depending on what class you were in, your paper may say something different, but this is from periods 5 and 6. Okay, and then we did our final practice problems. So in the first problem, we had the bag containing 3 purple, 7 pink marbles, and I drew it out for you. Remember, this started out as a purple marble. Okay, since it said that we're going to draw, or each marble selected is not put back into the bag, not put back into the bag means that it is going to be dependent because it's not replaced. So because it's dependent, that means your total changes or your denominator changes. So we're looking for the probability of selecting 1 purple and then 1 pink next. So that's why we put the probability in parentheses, purple and pink. Okay, so it says that we want the probability of a purple and then a pink, but it's not going to be placed. So that means when I first looked at my list, I had all 10 of these that were here. When I pulled my purple, I pulled out of 1, 2, 3 purples. So that's where the 3 out of 10 came from. Now, once I pulled my purple, I crossed it out. And then, after that, I was looking to pull a pink. So when we look at this, I still have all 7 pinks. But now there's only 9 total marbles to pull from. So that's why we had 7 ninths here. That was a 9. And since I simplified first, I took the 3 and the 9 and divided them both by 3. So that's why I have a 1 here because 3 divided by 3 is 1, and 9 divided by 3 gives me this 3. So now I'm actually multiplying this 1 times this 7 to get the 7, and this 10 by this 3 to get the 30. Had you done it the other way, you would have ended up with 21 over 90. Once you divided both of those by 3, you'd still get 7 over 30. Number 2, we have, excuse me, box containing 3 white marbles, 4 black marbles. Okay, and I drew it out for you. So these were black, in case you can't see. Okay, and then it said, what's the probability of drawing 2 black marbles and 1 white marble? Well, that's 3 marbles total. 2 black and 1 white. So that means we should have 3 words written. So the 2 black means write black twice. So that means a black and then another black and then the white. So that's why in parentheses it says black and white. So, now look at our probabilities. When I started out, remember, nothing was crossed out to begin with. So I had 7 total, and these 4 were black. So I first had a probability of getting 4 out of 7 blacks. Okay, since it said without replacement, that made it dependent. So my denominator should change the next time. So that's why I'm not going to replace it. So I crossed out the first one. So I'm going to just cross it out like that. So that one's gone. So now what I'm looking at is these 6 that are left. Ignore the X right now because I'm on the second part. So now I'm still looking to get a black again. So I have 1, 2, 3 that are still black out of the 6 altogether. So that's where this 3, 6 comes from. Since I'm not going to replace that black, I get rid of it. So it was crossed out. So now all I can see is these 5 that are left. I want a white one now. I see 3 whites out of the total 5. So that's where the 3/5 comes from. So now I solved it and I simplified first. So since I saw I had 3 6, I made that become 1/2. Then I saw that I had a 2 here and a 4 in the numerator. So that would simplify because I can divide them both by 2. So when I divided 2 by 2, it became 1. And when I divided 4 by 2, it became 2. So now I actually multiplied the 2 times the 1 times the 3 to get 6. And the 7 times this 1 times this 5 to get 35. Okay, problem number 3. Says slips number 1 through 9 were placed in a box. So we wrote out the sample space 1 through 9. Okay, 2 slips are drawn without replacement. So there's the part telling you dependent. Denominator changes. What is the probability that part A wants both are red? Remember the word both means you got to have 2 of them. So that means if both are red, both are odd, then that means I'm looking for an odd first and then an odd again. So that's why we have the probability of odd and odd. So when I first looked at my sample space, I circled all the odd numbers, 1, 3, 5, 7, and 9. That's 5 numbers that are circled out of the total 9. So if I pull out one of these odd numbers and I don't replace it, the second time around, for me getting an odd, I only have 1, 2, 3, 4 left. And there's only 8 numbers left now. So therefore, I have 4 out of 8 chance of getting the odd number the second time. So since 4 eighths simplify to 1/2, I multiply 5 times 1 to get 5 and 9 times 2 to get 18. And that's the probability. Part B, we wanted both even numbers. So since we had the probability that they're both even, remember again, both means I've got 2 of them. So therefore, it means the first has to be even, the second also has to be even. So that's the probability of even and even. Again, do not forget, if you do not write this part with your words in parentheses, I'm counting off. So now let's go back to our sample space. Since I first circled odd, that means everything that's not circled is even, right? So the probability of getting an even number would be 1, 2, 3, 4 that aren't circled out of the total 9. So that's why I first have 4 ninths. And means to multiply. And then, since I have taken away one of the even numbers, because it said don't replace it, now when I look through my sample space for another even number, I only have 3 left. And there's 8 numbers left. So that's where this 3 eighths comes from. Now, I simplified first. So since I saw the 4 in the numerator and the 8 in the denominator, that's like having 4 eighths, which simplifies to 1/2. Then I was left with a 3 in the numerator and a 9 in the denominator. That's like 3 ninths, which simplifies to 1/3. So that's how I ended up with 1 times 1, which is 1, and 3 times 2, which is 6. Had you not done it this way, you would have had 12 over 72. Divide them both by 6, you still get 1/6. Okay, final page, number 4. Let's see it for you. Let me get down here. Oh, that doesn't help. Okay, now I'll see what I have to do. All right, there we go. Okay, so number 4, I have a bag containing 3 red, 2 white, and 6 blue marbles. And we want the probability of drawing in order 2 red, 1 blue, and 2 white. So this one was also a dependent probability because it didn't say that I'm putting anything back. So again, denominator changes. Didn't write that in class, so write it now. Okay, so since we want it in this order, then that means we're looking for the probability of red and red for the 2 red, and blue, and white for the 2 white. So that's 5 probabilities altogether. I mean, your numbers add up to 5, don't they? So it means you should have 5 words written. So add them all together. 3 plus 2 plus 6 is 11 total. So when we get down to our probabilities, and I even drew this one for you as well. So I started with my 3 red, my 6 blue, and my 2 white. Okay. I first, excuse me, am going to look to see out of all these 11 how many reds I have. There's 3. So that's where the 3 11s comes from. Okay. Since I'm not replacing anything, I'm going to take away that red. Now I want red again. So there's 2 reds that you still see out of 11 altogether. So now I'm going to take away another red. So So once I cover that other red up, I now only have 9 left. So this second probability was 2 out of 10. Okay, now I've got 9 left that we can see all together. This time I want a blue. I have all 6 of the blues here. So that's why we had 6 ninths. But it tells me I'm going to take this blue and I'm not going to replace it. So once I cover that up, I now have only 8 numbers showing marbles. And now it wants a white. So I had these 2 whites that were showing. So that was 2 out of the 8 that you see. Now, since I took one of those whites, cover it up, I only see 7 left. So this time, my chance of getting a white is only 1 out of those 7 that we see here. So we know we did it correctly in our denominators with it being dependent because each time the denominator went down 1. And that's what you should look for with dependent probability. Denominator should go down 1 each time. So I simplified all my numbers and I got 1 over 770. If you need me to explain the simplifying, I'll do so very quickly. 2/10 simplified to 1/5. 6/9 first simplified to 2/3. So that's what these numbers were. 2/8 simplified to 1/4. That was a 4 first. Then I kept looking and I still had this 2 here and this 4 here. So I simplified them both by dividing by 2. So that's how I ended up with this 1 and this 2. Then I saw I had a 3 here and there was a 3 right here. Well, both of those divide by 3. So that's how I got this 1 and this 1. So that's how I end up with all the numbers that I multiplied together. And you can see my work right over here on the side for how I got the 770. 11 times 5 times 1 times 2 times 7. Okay, number 5. We had the 15 airmen, and it said that, excuse me, they put 1 through 15 in a hat and decided whoever drew divisible by 5 would get the coffee mess, and whoever drew 1 divisible by 4 would get the cleanup. So we listed out our sample space 1 through 15. And then we went and did the probabilities. It said the first person draws 4, the second draws 3, the third draws 11. And now we're trying to find the probability of what the fourth person is going to get. So the first one, the probability that the fourth person got the coffee mess. So that means we got to have 4 probabilities written. If the first one drew a 4, that means we're going to write the probability of a 4. And since the second one drew a 3, probability of a 3. And the third one drew an 11, so probability of 11. And the fourth one got the coffee mess. So remember, coffee mess said it's divisible by 5. So that's why I wrote divisible by 5. Now we go in and put our probabilities. Okay, since these are people going and pulling numbers out, they're not going to put their number back in when they're done. So they pull their number and keep it. So this problem is dependent. There's no replacement. So your denominators are going to change. So therefore, the first time a probability of a 4, there's only one 4 out of the whole entire 15 numbers. So that's where 115 comes from. Once we take out that 4, we've got 14 numbers left. There's only one 3. So that's where this 1 comes from. It's 1 out of 14. So now, once we've taken out that 3, we're down to 13 numbers. Next person comes up, draws an 11. There's only one 11. That's where this 1 comes from. And then that fourth person comes up, and he's going to try to draw a number divisible by 5. So, since the 5, the 10, and the 15 are still there, there are 3 numbers that are divisible by 5 out of the 12 that remain. So the 312 simplified to 1/4, and I punch these numbers in on the calculator to get 1 over 10,920. Part B, we wanted the fourth person to get the cleanup. So that means the first 3 people did the same exact thing again. But now we're trying to get the fourth person to get the cleanup. And remember, cleanup said it's divisible by 4. So that's why the first 3 you see are the same, but the fourth one changed to divisible by 4. So we still have the same first 3 probabilities, but now divisible by 4, when I go look up here, I've got 4, 8, and 12 that are divisible by 4. But notice 4 has been already pulled. So 4 is gone. That takes us down to only 2 numbers now. Only 8 and 12 are the remaining numbers that are divisible by 4. So that leaves me with 2 out of 12 numbers. That simplifies to 1/6. And I punched it on the calculator to get the last part. Okay, last problem is number 6 and 7. On number 6, we had the box containing 3 red, 4 green, 5 blue. It said 1 is drawn and then replaced. So if it's replaced, that means it's independent probability. The denominator is not going to change. So the probability of first getting a red and the second being a blue, right in parentheses, red and blue. Since we started out with 3 plus 4 plus 5, that's a total of 12 altogether. So the probability of my red is 3 out of 12. That's the 3 that was crossed out. And since that's simplified to 1/4, that's why I have 1/4 sitting over here. Now my probability of blue, there are 5 blues. And since that first red was put back in, I still have 12. So that's why I have 5 12s. Multiplying, you get 5 48s. Number 7, we have 5 red, 9 blue buttons. Randomly select the button, took it out of the box, and then selected another. Did not say we put it back in the box. So that means we didn't replace it. It's dependent probability. Denominator is going to change. So it wants the probability that both buttons are red. Remember, both means 2. So that means red and a red. So since there's a total of 14 buttons, 5 plus 9 is 14, then my first probability of getting a red is the whole 5 out of the 14 total. Now, since I already took out a red and didn't put it back, there's only 4 red the second time around. And I didn't put the first one back, so there's only 13 total the second time around. So that's where we get 4 13s. I simplified the 4 and the 14 by dividing them both by 2. So 4 divided by 2 is 2. 14 divided by 2 is 7. Once we multiply the numbers together, 5 times 2 is 10. 7 times 13 is 91. And that's what we did in class today. So hopefully this video helped you to review what we did and understand a little bit better. Now redo your homework and bring it in with an A on it tomorrow. See you later.